the solution. So we first have to understand some pretty basic concepts. So a palindrome. A palindrome is a number, an integer that reads the same forwards as backwards. So an example of this would be 393. And that's a 3-digit palindrome. And it reads the same forwards as backwards. So if we start from here, we read it as 393, and if we start from here, we also read it as 393. And another example would be 5005, and that is also palindrome. So again, we start from here, and we read it as 5005. We also start from the backwards, which is starting from this side, the units digit, and we also read it as 5005. So we want to make sure that you understand what a palindrome is. And also set some restrictions between 1,000 and 10,000. So if a number is between 1,000 and 10,000, how many digits does it contain? So 9,999 is the largest number, and the smallest number is 1,001. So we know that every number in between and included in 1,001 and 9,099 has to be inclusive, has to be a 4-digit number. So if it's 4 digits, we have 4 digits right here. And what we're trying to find is that if the palindrome is divisible by 7. So if a 4-digit palindrome is divisible by 7. So we can first name each digit as a variable. Okay, so we're going to first name the first digit as A. So it could be a number A. And we already know the last digit too, because if it reads the same forwards and backwards, that means we read the first digit as A and the last digit also as A, because we're starting from both places and they have to be the same. Okay, so and then we can go on to this is the units digit, and this is the hundreds. This is the thousands digit. Thousands digit. Okay. And then we can name the hundredths digit as B, so another variable B. And A and B can be the same, so A can be equal to B. And the reason why A can be equal to B is because there's no restriction in saying it. So we know that A can be equal to B. It just like the variable is different, but we'll just make sure that we know that. Okay, so since B is the hundredths digit, we also know that the tens digit is also 100. Is also B, because it has to be the same as the 100 digit. So when we read this number, forwards first, A B B A, and we read it backwards, which is also A B B A. So we want to make sure that we have a parallel, and if we divide it in half right here, if we divide this number in half between the thousands, hundreds, and tens in units digit, then we see that it is parallel and equal. Okay, so we have this number ABBA, and we can start finding the probability. But first, we want to make sure that we understand each value of each variable and each digit. Okay, so A, we'll start on the left-hand side. A. So how much is A worth? So if A is a digit, let's just say 9. Okay, we'll set an example. This is not the actual palindrome, but we have 9,000 right here. If we have the digit 9, how many tens is it worth? So it's 10 to the power of, this is 10 to the power of 0, is worth 10 to the power of 0. We can just rewrite it in the in base system. So 10 to the power of 2, that means 9 is 10 to the power of 3. So basically, it's worth 9,000. And we have the digit right here times how much the digit is actually worth. So since this is base 10, we don't have to make it too confusing. We don't have to include bases, but just make sure that we know how much that 9 is worth, which is worth 9,000. Okay, so we can set it. We can also work with that in our uh, actual problem. And as you see here, so this is the thousands digit. So that means A is one digit, a one digit, zero through nine. It can't be zero, but we'll figure that out later. It has to be one digit, and A time is worth uh, 1,000. So A times 10 to the power of 3. And then B is worth 100. So B times 100, which is 10 to the power of 2, is its actual value. Now, the tens digit, we have B again, and it's worth 10. So times 10. So if we have 5 for the digit, that means it's the entire tens section is worth 50. Okay. And then we can also write A as 10 to the power of 0, which is just 1. So, which is just A. And if we add up all the A's of the entire number and how much is A is actually worth, so we can add up the thousands digit and the thousands place and value and the units value, and if we add them up, we have 1,000A plus 1A, which is just 1,001A, and if we add the B's up, it's 110B. And so if we have an example here, let's just say A is equal to 9, B is equal to 1, then we have 9119. And if we just plug it in right here, if we plug A and B in, then we'll have 9119 come out. We just simply rewrote this entire thing. Instead of one large just number in general, we wrote it as 4 different numbers with different amounts. Okay, so 1001A plus 110, and we're finding if it's divisible by 7. So as you see here, 1001 divided by 7 is equal to 1304. We just do long division, 28 to 1. So 1001 is divisible by 7. So if we put any value for A in, we'll know that's automatically divisible by 7, because 1001 is just primarily just divisible by 7 in the first place. So any number we multiply just really doesn't matter. So if we had just like 2 in, it would still be a multiple of 7. So yeah, so we don't have to worry about 1001A. All we have to worry about is 110B. And 110B, since the first 1001A is already divisible by 7, we want to make sure that 110B has to also be divisible by 7 in order for the entire number to be divisible by 7. See, if we have 7 plus a number that's not divisible by 7, so 7 plus 2, which is 9, 9 is not divisible by 7. But once we add a number divisible by 7, like 21, then we know that is also divisible by 7. That's how it works. So we're going to make sure that 110B is divisible by 7. And 110B, if it's divisible by 7, there's two digits that actually work. One is 0, because if we multiply 0 by 110, then we get 0. And since we already have something divisible by 7 in the first place, that means we know that it's divisible by 7. Okay, and the second one is obviously 7, because we multiply and we get something divisible by 7. We add it to the 1001A that is divisible by 7, and we get something divisible by 7. So there's two digits that work. And since A's probability has already been found out, everything about A works. So any digit that we put in as A works, and we just have to find the probability that the number digit that we put in for B also works. So B, there's a total of 0 through 10 digits. 0 through 9. We can choose any digit from 0 to 9, and the reason why is because It's not in the hundreds, not in the thousandth digit, so it can be zero, and it can be any other number. So there's 10 choices for uh, for B, for the digit B, and two of them, as we found out, 0 and 7 are the only ones that work. So two of them work. Only two of them work. So that is equal to 1/5. The answer is E.